I have two equations on my desk tonight, and I am not allowed to use a calculator. The first one, x to the power of x equals 2. What number raised to itself gives 2? The second one looks friendlier. 2 to the power of x equals x squared. By the end of tonight, I want every solution to both. Exact answers where exact answers exist. And where they don't, I want digits, as many as I have patience for, earned by hand. No skipped steps. No, the rest is left as an exercise. If a number shows up on this desk, we will watch it get born. Let's dive in after the break. Welcome back. Okay. Deep breath. Puzzle 1. Cap x to the x equals 2. Honestly, my first instinct isn't algebra. It's just to play. Let me try numbers. Try x equals 1. 1 to the 1 is 1. Too small. Try x equals 2. 2 to the 2 is 4. Too big. Oh, that's already something. The answer, whatever it is, lives between 1 and 2. And in that region, the function can only climb. And I can prove it in one breath. Take any two numbers past 1, a smaller and a bigger. Raise the base first, exponent held fixed. A bigger base to the same positive power is bigger. Now raise the exponent, new base held fixed. A base above 1 to a bigger power is bigger again. Two moves, each one strictly upward. So the smaller input always loses. X to the x is strictly increasing past 1, which means exactly one crossing. Let me squeeze it. Halfway. X equals 1.5. So I need 1.5 to the power 1.5. Wait, what does that even mean? A number to a whole power, fine, repeated multiplication. But a number to the power 1.5? Okay, think. 1.5 is 1 plus a half, and a power of a half is a square root. So 1.5 to the 1.5 is 1.5 to the 1 times 1.5 to the half. It's 1.5 times the square root of 1.5. Oh, that's lovely. I can do that. Square root of 1.5 by hand. I'll guess and improve. Guess 1.2. Square it. 1.44. Too small. Guess 1.25. Square it. 1.5625. Too big. Guess 1.22. Square. 1.4884. Slightly small. 1.225. 1.5006. So the square root is just under 1.225. Push one more digit. 1.2247. Square it. 1.49989. Close enough to taste. Square root of 1.5 is about 1.224745. So 1.5 to the 1.5 is 1.5 times 1.224745. Multiply it out. 1.837117. 1.837. Less than 2. So the answer is above 1.5. The squeeze is now between 1.5 and 2. Next test, x equals 1.6. 1.6 to the power 1.6. Same trick? 1.6 is 1 plus 0.6. And a power of 0.6 is what? A 10th root raised to the 6th power? Do I want to compute a 10th root by hand?
No, I do not.
And this, right here, is the moment the whole game changes. Because I've hit a wall that every scientist before the 20th century hit. Weird exponents are brutal. And the tool they invented to smash that wall is the logarithm. Let me build it from nothing, because I promise no stone unturned. There's a special number called e, about 2.718. You can think of it as the natural growth constant, the base that calculus loves. Every positive number can be written as e raised to some exponent. 2, for example, is e raised to roughly 0.69. 10 is e raised to roughly 2.3. The natural logarithm, written ln, is just the exponent extractor. ln of 2 answers one question. E to the what equals 2? And here is why that's a superpower. Exponent rules say when you multiply powers, you add exponents. So the log of a product is the sum of the logs. And the log of a power, a to the b, is b times the log of a. Logarithms convert multiplication into addition and exponentiation into multiplication. They demote every operation one level of difficulty. But wait, I said natural log of 2 is roughly 0.69. Roughly? Tonight we don't do roughly without receipts. Where does that number actually come from? Can I compute natural log of 2 by hand right now? I can. There's a classic series and I'll grind it. The log of 1 plus x over 1 minus x equals 2 times x plus x cubed over 3 plus x to the 5th over 5, and so on, odd powers, odd denominators. Now pick x so that 1 plus x over 1 minus x equals 2. That needs x equals 1/3. Nice small number, so the series will converge fast. So, natural log of 2 equals 2 times the sum of 1/3 plus 1/3 cubed over 3 plus 1/3 to the 5th over 5, and on. Let me actually compute the terms. First term, 1/3. 0.333333. Second term, 1/3 cubed is 1/27th, about 0.037037. Divide by 3, 0.012346. Third term, 1/3 to the 5th is 1 over 243. Divide by 5, 0.000823. Fourth term, 1 over 2,187 divided by 7, 0.000065. Fifth term, 0.000006. Add them up, 0.346573. Double it, 0.693147. 5 terms. Pencil and paper. And I have natural log of 2 to 6 decimal places, 0.693147. That number is going to follow us around all night, so I'm writing it at the top of the page like a trophy. Right, back to the hunt, now armed. 1.6 to the 1.6. Take the log. That's 1.6 times natural log of 1.6. And natural log of 1.6? Same series, new target. 1.6 is 8 over 5, and logarithms turn that ratio into a subtraction of logs I can grind exactly like I ground natural log of 2. Do it, and it comes out to 0.470004. Multiply by 1.6, 0.752006. So 1.6 to the 1.6 is e raised to 0.752, which works out to about 2.121 over 2. So the squeeze tightens. The answer is between 1.5 and 1.6. Try 1.55. Natural log of 1.55 is 0.438255 times 1.55, 0.679295. E to that is about 1.972, just under 2. Squeeze again, between 1.55 and 1.6. Try 1.56. ln is 0.444686 times 1.56, 0.693710. E to that, about 2.0011. Barely over. So the answer is between 1.55 and 1.56, hugging the top. Around 1.559, maybe. And now I have to be honest with myself. This works. This will give me digits forever. But every single digit costs me a fresh logarithm and a fresh exponential. It's a shovel, and I'm digging a tunnel one spoonful at a time. What I want is different. I want to understand the answer. I want, if the universe allows it, a formula. So let's stop hunting and start doing algebra. X to the x equals 2. Take the log of both sides. Log of a power pulls the exponent down front. So x times natural log of x equals natural log of 2. Progress? The double-decker x is gone. But now x is standing outside and also trapped inside a logarithm. I traded one tangle for another. Let me try to untangle with a substitution. The annoying part is natural log of x, so give it a name. Let u equal natural log of x. Then x itself is e to the u. Substitute both. E to the u times u equals natural log 2. So u times e to the u equals 0.693147. Stare at that. U appears twice. Once as itself, once up in an exponent. Can I isolate it? Take a log. I get natural log of u plus u equals natural log of 2. The u is still in two places, one of them inside a log now. The tangle just moved. Divide, substitute, exponentiate. Whatever I do, it moves, but it never dies. And it turns out that's not me being clumsy. It is provable that no finite combination of school operations, plus, times, powers, exponentials, logarithms, will ever isolate this u. So the toolbox is genuinely missing a tool. Fine. Tonight we forge it ourselves. Here's the plan, and it's sneakier than it looks. What do I actually do when I solve x squared equals 5? I apply the square root, the inverse of squaring. When I solve e to the x equals 5, I apply natural log, the inverse of exponentiation. Solving is applying an inverse. My equation says u times e to the u equals some number. The thing being done to u is the operation. Take a number, multiply it by e raised to itself. If I understood that operation completely, its inverse would hand me u on a plate. So let's interrogate the function f of w equals w times e to the w. Everything about it. At w equals 0, 0 times 1, 0. It passes through the origin. For w positive, both factors positive, both growing. It climbs to infinity, fast. For w negative, w is negative, e to the w is positive, so the product is negative. The whole left side of this curve lives underwater. And far to the left, as w heads to negative infinity, two forces arm wrestle. The factor w pulls down to negative infinity. The factor e to the w shrinks toward 0. Who wins? Try w equals negative 10. E to the negative 10 is about 0.000045, times negative 10 is about negative 0.00045. Basically 0. The exponential wins, it always wins, and the product sneaks back up toward 0 from below. So follow the shape with me. Far left, hugging 0 from underneath. At 0, exactly 0. In between, negative, which means the curve must dip down and come back up. There is a lowest point down there, a bottom of the valley. Where? At the bottom of any smooth valley, the slope is 0. So I need the slope of w times e to the w. This is a product, so I need the product rule, and since we're assuming nothing tonight, let me show you why the product rule is true in 30 seconds. Nudge w by a tiny amount, call it h. The new value is w plus h times e to the w plus h. And e to the w plus h is e to the w times e to the h, and for tiny h, e to the h is almost exactly 1 plus h. Multiply everything out and drop the h squared term. Not because I'm cheating, because it vanishes in the limit as the nudge shrinks to nothing. The change comes out to h times e to the w plus w e to the w. So the slope, change over h, is e to the w times 1 plus w. Look how clean. Now e to the w is never 0. Never. So the slope is 0 at exactly one point in the entire universe. W equals negative 1. The bottom of the valley is at w equals negative 1, and its depth is f of negative 1, which is negative 1 times e to the negative 1. Negative 1 over e. About negative 0.367879. That number is a law. No input on Earth makes w times e to the w dip below negative 1 over e. Remember it. Now solve w e to the w equals c by drawing a horizontal line at height c and counting hits. If c is 0 or positive, 1 hit, out on the rising arm. One solution, always. If c is between negative 1 over e and 0, the line slices through the valley and hits the curve twice. Two solutions. File that away, it will detonate later tonight, I promise. If c is below negative 1 over e, no hits. No solutions at all. And so the inverse function is born. For any c that's allowed, define w of c as the answer to w times e to the w equals c. On the two-solution strip, there are two versions, w0 from the valley's right wall and w minus 1 from the left wall. That's the whole invention. It's called the Lambert W function, and you and I just built it from a product rule and a valley. So my puzzle answers instantly in symbols. U equals w of natural log 2. And since x is e to the u, x equals e to the w of natural log 2. There it is. The exact solution of x to the x equals 2. But hold on. Hold on. I can hear the objection because I'm making it myself. That's not an answer, that's a name. W of natural log 2, what is it? If I can't turn it into digits with my own two hands, I've just hidden my ignorance inside a fancy letter. So now comes the real test. Can this new function be computed, by hand, faster than my old spoonful-at-a-time shovel? Oh yes, spectacularly faster. The method is Newton's, and the idea is pure geometry. I want the w where the curve we to the w crosses height 0.693147. I make a guess. At my guess, the curve has a value and a slope, and I know both. So I slide along the tangent line, the straight line that kisses the curve at my guess, until that line hits the target height. Straight lines are trivial to solve. Where the line lands becomes my new guess. Repeat. The recipe, in symbols. New guess equals old guess minus the error divided by the slope. And we computed the slope formula already. E to the w times 1 plus w. Everything is in place. Let me guess w equals 0.5 and grind the first step completely. I need e to the 0.5. By hand. The exponential has its own series, the most famous in mathematics. E to the x is 1 plus x squared over 2 plus x cubed over 6, factorials forever. Feed in 0.5. 1 plus 0.5 plus 0.125 plus 0.020833 plus 0.002604 plus 0.000260 plus 0.000022. Running total 1.648721. 7 terms, 6 decimals. E to the 0.5 is 1.648721. Now the Newton bookkeeping, line by line. Value, w times e to the w, is 0.5 times 1.648721, which is 0.824361. Target, 0.693147. My error, plus 0.131213. I overshot. Slope, e to the w times 1 plus w is 1.648721 times 1.5, which is 2.473082. Correction, error over slope. 0.131213 divided by 2.473082 is 0.053057. New guess. 0.5 minus 0.053057 equals 0.446943. One step done, every stroke visible. Step 2, same dance, and here's a professional trick so I don't need a fresh series from scratch. E to the 0.446943 is e to the 0.5 times e to the negative 0.053, and that tiny exponential is just 1 minus 0.053 plus a crumb. Multiply by my stored 1.648721, and I get 1.563526. Then, value 0.698807. Error plus 0.005660. Tiny already. Slope 2.262333. Correction 0.002502. New guess 0.444441. Step 3. Value 0.693159. Error plus 0.000012. 12 millionths. Correction 0.000005. New guess 0.444436. And step 4 changes nothing in the first 9 decimals. It has converged. Watch the errors fall. 0.13, then 0.0057, then 0.000012, then nothing. Each step roughly doubled my correct digits. 3 steps of honest arithmetic bought me what the bisection shovel would have needed dozens of logarithms to reach. So, w of natural log 2 equals 0.444436. Last move. X equals e to the u. Another exponential series? No, wait. Wait. Look at the definition. U times e to the u equals natural log 2. So e to the u, the exact thing I want, equals natural log 2 divided by u. The definition hands me the answer as a division problem. X equals 0.693147 divided by 0.444436. Long division, the actual kind. It goes 1.559610. And the verdict on puzzle 1? X equals 1.559610. Right where our squeeze said it must live, between 1.55 and 1.56, hugging the top. Check it. X times natural log of x should equal natural log of 2. And natural log of x is u. That was our substitution. So the check is 1.559610 times 0.444436. Multiply it out. 0.693147 to the last digit. Sold. Puzzle 2. 2 to the x equals x squared. And I'll confess, this one looks easier, so my guard is down. Let me just try small numbers again. X equals 2. 2 squared is 4. 2 to the 2 is 4. 4 equals 4. It's a solution. First try. X equals 3. 2 cubed is 8. 3 squared is 9. Close, but no. X equals 4. 2 to the 4th is 16. 4 squared is 16. Another one. 2 solutions, both whole numbers, 0 effort. What a friendly little equation. So, done? Something's itching, though. Puzzle 1 taught me these mixed equations, polynomial fighting exponential, hide their structure. Let me at least look at the whole battlefield before declaring victory. Picture both curves, the parabola x squared, the exponential 2 to the x. For big positive x, the exponential wins. It always wins eventually. They cross at 2 and at 4, fine. But what about negative x? The parabola on the left side rises. It's a bowl. And the exponential? 2 to a negative number is small but positive, decaying towards 0. So at x equals 0, exponential is 1, parabola is 0. Exponential on top. At x equals negative 1, exponential is 1/2, parabola is 1. Parabola on top. They swapped. Somewhere between negative 1 and 0, the curves cross. There's a third solution. Hiding on the negative side, and it is definitely not a whole number. I actually gasped. Okay, hunt first, understand second. Bisect it. X equals negative 0.5, 2 to that is 1 over root 2, 0.707107. The square is 0.25. Exponential on top. X equals negative 0.75. Exponential gives 0.594604. Square gives 0.5625. Exponential still on top, barely. X equals negative 0.8. Exponential, 0.574349. Square, 0.64. Parabola on top. crossing between negative 0.8 and negative 0.75. X equals negative 0.77, exponential 0.586417, square 0.5929. Parabola still on top, whisker close. So the root lives between negative 0.77 and negative 0.75, around negative 0.76 something. Enough shoveling. We own a power tool now. Let's do this exactly. Take 2 to the x equals x squared and take square roots of both sides. Careful, careful. The square root of x squared is not x. It's the absolute value of x. That single detail is where the third solution has been hiding all along, so I refuse to gloss it. Case 1, x positive. Then absolute value of x is just x, and the equation becomes x equals 2 to the x over 2. Write the right side with e. 2 to the x over 2 is e to the x over 2 times natural log 2. So, x equals e to that. Now herd everything to one side. Multiply both sides by e to the negative of that exponent, x, times e to the negative x natural log of 2 over 2 equals 1. Stop. Sit with that line for a second because it is strange. A moment ago I had a clean equation about doubling and squaring. 2 legal moves later, a rewrite and a multiplication, and x is standing next to an exponential with x living upstairs, the whole thing equal to 1. Nothing was broken. The puzzle is confessing what family it belongs to. Now look at the shape. Something times e to the something, but the somethings don't match. Outside sits x, upstairs sits negative x natural log of 2 over 2. Make them match. Let t equal the upstairs thing. T equals negative x natural log of 2 over 2, which means x equals negative 2t over natural log of 2. Substitute the outside x. Negative 2t over natural log of 2 times e to the t equals 1. Multiply both sides by negative natural log of 2 over 2. T times e to the t equals negative natural log of 2 over 2. There it is, our function's signature shape. And the target number is negative 0.693147 over 2, negative 0.346574. Now, the law. Nothing goes below negative 1 over e, which is negative 0.367879. Is our target above the floor? Negative 0.346574 versus negative 0.367879. Yes, above the floor, below 0. We are standing in the two-solution strip, the valley slice, the one I told you to file away. 2 values of t, which means 2 positive values of x. And wait, we already know 2 positive solutions, 2 and 4, from the guessing game. Are those the 2 branches? Standing there this whole time? Hold on. Before I reach for Newton and start grinding digits, let me just look at the equation. T times e to the t equals negative natural log of 2 over 2. If the answer were something clean, what would e to the t have to be? What is the one exponential value we truly own tonight, exactly? No series, no approximation. E to the natural log 2 equals 2. That's the definition of natural log 2. So e to the negative natural log of 2 equals 1/2. Exactly 1/2. So try it. Try t equals negative natural log of 2. The product becomes negative natural log of 2 times 1/2. That's negative natural log of 2 over 2. That's the target. That is exactly the target. Dead center, no decimals harmed. T equals negative natural log of 2 solves it on the nose. And the x it produces, negative 2t over natural log of 2, is negative 2 times negative natural log 2 over natural log 2. The natural log 2's cancel each other completely, like they were never there. X equals 2. My lucky guess from 10 minutes ago just walked back in, wearing a formula. But that's one branch. The lower branch is still out there, some t below -1. Same question. Can e to the t be something we own exactly? If 1/2 worked, what about 1/4? E to the t equals 1/4 when t equals -2 natural log of 2. Test it. The product. -2 natural log of 2 times 1/4. Negative natural log of 2 over 2. The target again. And it's x, -2 times -2 natural log of 2 over natural log of 2. Cancel. 4. Exactly 4. I need a second to enjoy this. The function we forged for Puzzle 1 just explained Puzzle 2's coincidence. 2 and 4 aren't random lucky integers. They are the two walls of the valley, the two branches of one inverse function, evaluated at negative natural log 2 over 2. The equation was showing us w's double-valued strip all along, and we mistook it for luck. And notice where they sit, 2 and 4, straddling the special point 2 over natural log 2, about 2.885. The geometry predicted there would be two solutions. That was the valley's promise. The neatness is a separate gift. The algebra reveals that in this special case, both branch values happen to collapse into exact multiples of natural log 2. The valley guaranteed the count. The equation supplied the elegance. Case 2. X negative. Absolute value of x is -x. So, -x equals 2 to the x over 2. Same herding, same substitution. T equals -x natural log 2 over 2, and this time the minus sign flips the target. T times e to the t equals positive natural log 2 over 2. Positive 0.346574. Positive target, so exactly one solution. T equals w of 0.346574. No exact closed form this time. The universe isn't that generous twice in one night. So we grind. Newton, full bookkeeping, guessed t equals 0.3. E to the 0.3, by series, 1 plus 0.3 plus 0.045 plus 0.0045 plus 0.003375, that one terminates exactly, plus 0.000020. Total, 1.349859. Value, 0.3 times that, 0.404958. Target, 0.346574. Error, plus 0.058384. Slope, 1.349859 times 1.3, which is 1.754816. Correction, 0.033271. New guess, 0.266729. Breathe. We've been at this a while, so let the ritual carry us. Step 2. Same 5 lines, no rush. Value, 0.348265. Error, plus 0.001691. More than 30 times smaller in one step. Slope, 1.653952. Correction, 0.001023. New guess, 0.265707. Step 3, and watch how little is left to fix. The error is 1.5 millionths. New guess, 0.265706. Converged. The errors again, 0.058, then 0.0017, then millionths. Digits doubling every step, like clockwork. So t equals 0.265706, and x equals negative 2t over natural log 2. Negative 2 times 0.265706 is negative 0.531412. Divide by 0.693147, long division again, and out comes x equals negative 0.766665. Between negative 0.77 and negative 0.75, exactly where the bisection cornered it, hours of shoveling confirmed in one formula. But don't take the formula's word for it. Don't even take Newton's. Go all the way back to the original equation, the one from the top of the night, and make both sides testify separately. One side built from doubling, one side built from squaring. They have never met anywhere else on the negative axis. If our x is real, they must collide at it, digit for digit. 2 to the power negative 0.766665. Work it through the exponential, and you get 0.587775. X squared, negative 0.766665, times itself, 0.587775. The same number. Digit for digit for digit. Two curves, one born from doubling, one from squaring, agreeing to 6 decimal places at a point we located with a valley, a tangent line, and long division. So let's lay the trophies on the table. X to the x equals 2. One real solution. X equals e to the w of natural log 2. And by hand it is 1.559610. 2 to the x equals x squared. 3 real solutions. 2 of them exact and whole. X equals 2 and x equals 4, unmasked as the two branches, w0 and w minus 1, of negative natural log of 2 over 2. And one of them irrational and shy, hiding on the negative axis. X equals negative 2 over natural log of 2, times w of natural log of 2 over 2. By hand, negative 0.766665. And look at the chain we forged to get here, link by link. Square roots by guess and check. Logarithms built from a series. Natural log 2 earned to 6 decimals in 5 terms. A wall no algebra could pass. A new function, defined as the inverse of we to the w. Its valley mapped with one product rule. Its floor fixed at negative 1 over e. Its 2 branches counted with a horizontal line. Newton's tangent dance to turn the symbol into digits, doubling its accuracy at every step. And long division, humble long division, delivering the final answers. Every link forged in the open. Every number on this desk can be traced back to a pencil stroke you watched happen. That's the whole promise of this channel. Mathematics is a chain, and tonight, you inspected every ring. Both puzzles closed. Thanks for watching.